When I created my first state machine, it was as if a whole new world had opened up to me. I never thought that such a simple structure could help me write incredibly clean code that is also very easy to expand upon. Before I learned about state machines, my code for a character controller looked something like this. My player can stand still, walk left or right, jump, and fall back down. Just a simple and small script, right? But when I wanted to add a new mechanic, say crouching, I couldn't just check for a crouch input and play the crouch animation, because the animation would reset to its first frame due to earlier animation calls in the script. So naturally, like any new game developer would, I added a new variable to track when the player is crouching and used it in if statements to prevent certain parts of the code from executing. This code was still pretty easy to understand, but as I added more mechanics like a dive, a double jump or a wall jump, each mechanic also brought in new variables. My script ended up either packed with many nested if statements or full of conditions lined up next to each other. Over time, this buildup of variables and conditions made the code very messy and hard to debug. But that's where the state machine comes in. Its application isn't just limited to games or character controllers, it's widely used across various systems, and whether you are using Unity, Godot or Unreal, I even made one in Scratch, state machines will help us write clean and easy to understand code. So now that you know why we need state machines, the next question is, how does a state machine work and how do I build one? A state machine is a system that describes the behavior of something. That something in my case is the player, but for you it might be a simple enemy AI or something like a UI system. A state machine consists of a finite number of states, and only one of those states can be active at any given time. What makes the system so special is that it can switch between those states whenever a certain condition is met. Such a condition can be the press of a button, or more complex events like traveling a certain distance. And to put this a bit more into perspective, we can simply draw out the states. Let's take our player controller again before it could crouch or dive. Then we are left with three simple states: floor, jump and fall. Let's start with the floor state. During the floor state, our player can move left and right while playing a walk animation or stand still and play an idle animation. Our player can also decide to press the jump button. When this happens, we want to transition from the floor state to the jump state. So we'll write down an arrow to represent this transition. Then we have the jump state, in which the player can also move left and right, but it should start with an upward velocity that decreases over time. It should also play a jump animation. From the jump state, two conditions should cause a transition to the fall state. Either when we release the jump button, or when we are at the apex of the jump. Lastly, in the fall state, our player should again be able to move left and right, and their downward velocity should increase over time while playing a fall animation. Upon landing on the floor, we transition back to the floor state. For our three simple states, this state machine design looks pretty solid. However, we are missing a single transition that is easy to overlook. Can you tell which one's missing? Currently, when we walk off the edge of a platform, we are able to walk on air. And that's because we didn't add the transition from the floor state to the fall state upon leaving the floor. There's not exactly a right or wrong way when it comes to designing state machines. You'll often find me distributing the states into states such as the floor, fall and jump state. But you can also decide to split up the floor state in, let's say, two different states. For example, the idle and walk state. It's simple to represent a state machine using just guards and a few arrows. But what do they look like in code? We need a single variable to keep track of a value. Then inside the game loop, all we do is check if that value is equal to a number, and if true, run code that is specific to that number. Those numbers represent the states, and so far we've only defined state 0, state 1 and state 2. But we can define as many states as we need to. This is already the simplest basis for a state machine. Let's put it into practice by looking at an example. For this example, we will use the floor, jump and fall states to create a basic character controller. Just like before, create a variable, let's call it active state, to keep track of a number that will represent which one of the states is currently active. Inside the game loop, in the first line, I capture the player's input inside a local variable. Below that, we will write the actual state machine part. To determine what state we should run, we check if the value of active state is either 0, 1, or 2. Let's associate 0 with the floor state, 1 with the jump state, and 2 with the fall state. Then we define the movement for each state by adjusting the player's velocity. All 3 states should include moving left and right. This results in some duplicate code, but that's okay. The jump state should get an upward motion, and the fall state should be affected by gravity. Then we define the transitions between states. We can create a transition simply by assigning a new value to our active state variable. In the floor state, upon pressing the jump button, we should transition to the jump state, so we assign 1. Upon leaving the floor by walking off an edge, we should transition to the fall state, so we assign 2. In the jump state, unlike in the state machine we designed on the drawing board, for now we make an unconditional transition by directly transitioning to the fall state, so we set active state to 2. This way, the jump state acts like an impulse because it runs for only a single frame. In the next section, we'll add a condition to this transition. Then, inside the fall state, upon touching the floor again, we transition back to the floor state by resetting the active state to 0. For the Godot users under us, at the bottom, we add the move and slide function so our player actually starts moving. When we use this script on our character in-game, it works the same as it did before. We can move, jump and fall, but this time we've used a simple state machine design to accomplish it. We can actually improve the readability of this code by adding what's called an enum. Basically, an enum makes code more readable by replacing numerical values with words. So if we add an enum called state, we can add the values floor, jump and fall to it. Then, instead of setting the active state to 0, we can set it to state.floor. And for each if state condition and transition, we replace the numerical value with the corresponding enum value. There's one final step to improving readability, and that is replacing the if statements with a match statement, which in other languages might be known as a switch or case statement. In our game loop, we match against the active state. Then we move the scope of this section by adding an extra indent and replacing the if statements with only the appropriate state values. When you compare the updated code with the old one, you can tell how much cleaner the code looks now that we've added an enum to it. It's much easier to identify the states, and the enum values already give a short description of what a state is about. This so-called enum state machine is a great first step towards writing cleaner code. But it still has a small issue. What if we want to add animations to it? Adding walk and idle animations is easy because they loop endlessly. Just play the walk animation when direction holds a value and play the idle animation when it doesn't. But what about the one-time animations? If we were to add a fall animation inside the fall state, the game loop would call the animation on every frame. And that would result in this fall animation playing on repeat, even though it's not supposed to. So we need a way to call the fall animation only once. And maybe you already see a solution where you simply start playing the animation before switching states. But that would require you to call the animation for each transition to the fall state. And if you have many different states transitioning to the fall state, you would end up writing a lot of duplicate code. Fortunately, there's a more elegant solution to this problem. We are going to use the transitions between states to run one-time operations. Instead of assigning the active state variable directly, we will use a function called switchState for it. It takes the state we want to switch to as a parameter and assigns it to the active state like usual. Then we create the same match structure as we have in the game loop, and with it, we can determine what should happen when transitioning to a state. So for example, upon transitioning to the fall state, we want to play the fall animation. In our game loop, we can now simply replace all direct assignments of active state with the switch state function call. Currently, the jump state still acts as an impulse, transitioning to the fall state without waiting for a condition. The correct behavior for the jump state should be to start falling upon releasing the jump button or when the player reaches the apex of the jump, which can be checked by comparing the y velocity to 0. Since we now remain in the jump state, we should also apply gravity and set the y velocity to 0 before switching to the fall state. Instead of applying an upward motion during the jump state, we can now apply it upon switching to the jump state. Here we can also call the jump animation. The piece of code we've just added really shows the strength of the state machine and its transitions. The delayed transition from the jump to the fall state gives us more control over the height of our jump, and the new switch state function is great for adding one-time operations between states. To top it all off, let's make sure our player can turn around by flipping the sprite. Inside each state, check whether direction holds a value and flip the sprite when that value is smaller than 0. This is an extremely solid basis. This structure is very easy to expand and we can add new states to it in just 5 simple steps. Let's say we wanted to add crouching. We start by looking at where crouching belongs in our state machine design. When we look at the drawing board, I think crouching can only be done from the floor state upon pressing down the crouch button. Then, of course, if we release the crouch button again, we go back to the floor state. Let's say that when we perform a crouch, we keep sliding a bit into the walking direction. This means that if we start sliding too close to the edge of a platform, we can fall down from it. So from the crouch state, we can also transition to the fall state. For our first step, add crouch as a state to the state enum. As the second step, determine what should happen when we transition to the state. For crouching, we only need to play the crouch animation. Third, define the behavior during the game loop. To keep sliding forward, we just multiply the current x velocity by 0.9, so on every frame the horizontal velocity will be reduced slightly. For our fourth step, we add transitions from this state to other states. So if we no longer touch the floor, we should switch to the fall state. Otherwise, if we release the crouch button, we should switch to the floor state. In the final step, we add transitions from other states to this state. In our case, only the floor state should transition to the crouch state when the crouch button is pressed. And this should result in the desired crouching behavior. Just for the fun of it, let's add a dive in 30 seconds. Add dive to the enum. When transitioning to the dive state, play the dive animation. Set the x velocity to the input direction multiplied by 1.5 times the walk velocity, and the y velocity to half the jump velocity. In the game loop, we apply gravity and switch to the floor state upon touching the floor. Lastly, add transitions from both the jump and fall states upon pressing the dive button and when direction holds a value. And just like that, we have a functional dive. This enum state machine is an excellent way to learn programming, but it's not the only type of state machine. There's a more advanced inheritance-based state machine that gets a bit more complex than this one. It's also known as the state pattern, so let me know in the comment section if you'd like me to cover that topic as well. And now that you know the ins and outs of a basic state machine, why don't you try and test your new skills and implement one like I did in this video where I created a character controller like the one used in Hollow Knight Silksong.